Right. So, yeah, the fourth lesson that we have to discuss, the logic gates with Boolean functions. So, let's talk about like this. Now, first of all, you have to understand why there is, like, what is a logic gate and why there is a Boolean function kind of things there in the computing part, right? So I'll tell you the reason why, right? Because if you think about the environment or like the practical world, you may see different kinds of circuits, different kinds of scenarios in the environment, right? So as an example, a simple example, you can see when you are walking on the streets, or like when it comes to some home gardens, there are some lamps, right? So where you can find, hold on a second, I can't see my palette. Okay, so if you think about the garden lamps, right? So these kind of garden lamps are there, where you can see like when the sun is there, when sun is there, these lamps, right? They are off, right? But if you think about a situation where the environment gets darker, or like normally it will get with the night falls, or like due to a weather condition, if the surroundings is been getting darker, these things will be automatically on, right? So like there are situations where the light is there, where the light is not there, right? So when you don't have the light, so these things will get light up, right? You can clearly see that, right? So as an example, let's say it's the night time, right? So how this is happening, right? That will give you the idea where the logic gates have been involved, right? Now to happen this, inside this bulb, or like inside this circuit, inside the structure, there's a small circuit, right? These small circuits have sensors on it, right? So there are circuits. Inside the circuits, there will be sensors, right? So in this case, we use a sensor which is sensitive for light, right? The light intensity. So like how this sensor is going to work, it is given a particular logic to be operated, right? So what is the logic that they are like talking about is, so these sensors, they generally take the input, they sense the things, right? So according to the input that the sensor is receiving, it asks to do the output, right? It's asks to act with its output. Okay, so right, so as the input, it is the, let's call it light sensor, right? So this is the input, and the output is going to be the bulb, right? So it describes when light is available, when the light sensor, it calculates how big, or like what is the amount of light on the surrounding area, right? So the unit that they are usually using is lumens, right? Which is not in your syllabus. You don't need to worry about what are the unit of the light intensity, right? So the lumens, ආලෝක තීව්‍රතාව කියලා අපි කියනවා, right? So like in very simple terms, right? In the daylight, we can consider it as the daylight, or simply a day, and the night. Right, so on the day, bulb is on, and on the night, I'm sorry, during the day the bulb is off, during the night the bulb is on, right? So when they are creating this circuit, they are using this particular logic, right? And they are assigning particular values to these inputs. So they indicate day using the value 1, the night using the value 0, as an example, right? And the off state as 0, on state as 1, right? As you can see, like the states that they have taken are opposite to each other, right? So the day and night, we can say it is not the day, right? Right, and off and as well as on can be described as not off, right? It's always talking about a opposite condition, some particular condition and the opposite of it, right? Or the අපි එකට කියනවා නැත අර්ථය අරගන්නවා කියලා, right? It is day and not a day, that means night. It is off and not off, or it is on and not on. Right, so in Boolean algebra we always deal with the things using these two states, right, which have opposite values, right? So according to this particular scenario analysis, they will create some particular expression using the Boolean algebra, right? We are talking about this in the sector called Boolean algebra, right? And using that, they are deriving things called Boolean expressions, right? And using Boolean expressions, they are going to develop a circuit. What is the circuit? The circuit that we are talking about here, right? So the way they are figuring out what kind of a circuit that we should be included into the this particular bulb or like this particular lighting system is by analyzing the states that can happen with the bulb, right? And then using, like when they are developing the circuit, they are developing it inside an IC, right? This is kind of an IC. I think you have seen an IC. I think I have showed you when we are doing the first lesson, right? So if you can remember, this kind of a structure was there for an IC. It's a black color one which has pins around it. And there is a small cut over here, right? Something like this, right? If I show you an actual picture of the ICs, let me check. Yeah, there you go. All right. So this is a particular kind of a IC, integrated circuit, right? There are different types. And this is something which shows you what happens inside. So this particular structure or the plan is made out of this particular sketching, right? So according to this, due to this expression, first they develop a circuit. That circuit is kind of a conceptual diagram or like a particular diagram which shows what happens, what should be done inside the IC, right? And when we look into this kind of a picture, we can't see a specific thing inside here. We can see there are some wires, some copper things are there, right? The metals are there, right? So some copper wires are there. So using those copper wires, using some other elements, they have made it. That's the physical thing that we can see, the actual thing that we can see. But when we are planning this, we are planning in a different manner, right? If you can remember, if you I think you are drawing some electrical circuits in the science, right? You people are used to circuits like this, right? This indicates by the bulb. There are batteries, there are resistors, right? These kind of things are there, right? But we know this is the symbol of the bulb. It is not actually a bulb, although the physical bulb. Likewise, when we are developing the circuit in the Boolean algebra, we have to use different kinds of symbols. Some symbols are like this. Some are like this, right? Some are like this, right? They have some names as well. This is called not, this is called and, this is called O, right? Some funny names are there, right? So using these kind of symbols, they will create a particular circuit, and that circuit will be implemented in the practical world, in the actual world, in this manner, right? So in this lesson, what we are trying to do is, we are trying to develop a particular schematic diagram or like a particular plan using these types of symbols. Are we clear why we are learning the Boolean algebra or like the gates and all these stuff?
Sir.
Yeah, right. Okay. If you got any questions, you can ask. And now I'm going to jump into the lesson straight away. Right? Okay. Now, when it comes to the Boolean algebra, like the Boolean sector, right? To talk about the gate, there are two types of gates that we need to understand or that we need to introduce with, right? So when we are talking about the gates, we call it logic gates. There are two types. One particular type is called the basic gates. And the other part is called combinational gates. Right now, when it comes to the basic gates, there are three types. Actually, there are four types, but in your syllabus, we are only talking about three types. First one is called the NOT gate. Symbol goes like this. And the AND gate. Since the AND is ending up with a D, we can memorize AND gate is kind of the shape of D. AND gate. And finally, they got something called O gate. O gate is kind of a crescent. Right, and when it comes to the combinational gates, again, there are three types, but in your syllabus, you are given only two things, which is called NAND. And the other one is called NO. Right, so the NAND gate, it is something very similar to the AND gate, but there is a small difference. Right, okay. So these are the two types of gates that we need to learn about. Is that clear, everyone?
Sir.
Right. Okay, so let's write about the things. So let's have the heading, logic gates with Boolean functions. All right, so moving forward. Let me see what to be written. Yeah, you better write this particular one.
Sir, should we write that thing under logic gates?
No, no. It's better you write it under the main heading. It doesn't matter. Let me know when you are done, people. Okay, one is done. How about others?
Done, sir.
Right. Anyone who is still writing? All right. Moving forward. Yes. And then we can go for our this classification. So after that, we just draw this classification. Right. Two are done. How about others?
Answer.
Okay.
Wait a second, sir. I mean NAND and no.
Right, okay. Right, okay. Keep it up.
Done, sir. Okay, sir.
Right. Anyone who is still writing? Okay. Right. So now we need to identify what are the functions of these components, right? Or the logic gates, right? So first we are going to get to know about the basic gates, which is the NOT and an O, right? So we have this space. So now we are talking about basic gates. Right, so when it comes to the basic gates, there are three types, you know now it already, right? So the first one is called the NOT. Right, so the NOT gate can be drawn like this. And the left-hand side line is called the input line. And the right-hand side, it indicates the output. Right? And there is a particular function or like particular way that this NOT gate is working. Right? So we express that thing using a Boolean variable. So we say when A is provided to the NOT gate, it is going to provide you something called A bar. Or we can write it as A dash as well. What do you mean by this? What's happening, like what is A and what is A bar? That particular thing is described by a small table regarding a particular logic gate, which we call as a truth table, right? Truth table. So there, in the truth table, we indicate the inputs as well as the output. Now, since this is something that you can find inside the IC, and specifically when it comes to the computing, we know that computing happens in the basis of the binary number system, which means ones and zeros, which means again using the bits, right? So whenever some particular signal or some particular input is received by any gate, so in this any input line, it can receive either a 0 or a 1. Those are the simple inputs that a particular input line can be taken, right? So the purpose of the NOT gate or the operation of the NOT gate is when something received by a NOT gate is capable of inverting the input. Inverting means making the input to its opposite. That means when 0 is received at the input line, this output line will produce a 1. So it makes the NOT gate, this NOT gate, converts it to into its opposite. That is what we call inverting. If the input part, if this one receives a 1, then the output is going to become a 0. Simple as that. Are we clear with this, people?
Yes, sir.
Right. So this is what you call a truth table. Right. So you better remember, we are going to draw the truth tables for all the gates that we have learned. So it's better you remember a particular truth table regarding particular gates. So that is how the NOT is working. And after NOT, I'm going to talk about the AND gate. AND gate. So the AND gate, we know the structure is like this. It has 2 inputs and a 1 output. And when it comes to the AND gate, at least 2 inputs must be there, right? So in the gate structures, there is only one gate which has just one input. It is the NOT gate, right? It is not receiving more than that. It is not having less than that. Just one input and one output. All other gates has at least 2 inputs, and always they got only one output line. So according to the Boolean algebra, we say if A and B is given to these inputs, different inputs, its output is going to become or going to be performed as A dot B. A dot B. So we address this as a Boolean multiplication, something very similar to the mathematical multiplication, right? So if we think about the truth table, which explains what's happening inside the AND gate, we take the line A and we take the line B because we got 2 input lines. All right. I think something worse has happened.
So has here the writings been erased?
Yes, hold on. Let me undo it and see whether I can
Retrieve, sir.
find my things. Oh, that's bad.
So is it not there?
No, it's not. Oh, come on. Oh, that's bad. I still wonder how that happens. Like it happens so many times. I don't know what is. I think it's the erase that I'm touching always. Okay. Nope. Hold on. That's not good. Okay. No option. I have to draw it again. Give me a second, people. I will draw it quickly. Hanushi, we call it A bar, right? When A and a horizontal bar at the top of it, it is called A bar. Right. Okay. I think we were here. And yes. Now, when it comes to the two inputs of the AND gate, we can assume things are going to happen like this. When A is receiving a 0, B can also receive a 0. When A is receiving a 0, B can receive a 1. When A is receiving a 1, B can receive a 0. Or in other case, both A and B can receive a 0. So I told you, AND indicates a Boolean multiplication, right? It's a multiplication. So it's something very close to the mathematical multiplication. In your case, in your syllabus, it is very same to the mathematical multiplication. So it's easy for us to understand, right? So the output is going to be produced like 0 into 0 gives you a 0. 0 into 1 gives you a 0. 1 into 0 gives you a 0. 1 into 1 will only gives you a 1. Right? So that is something that you need to remember how this is working. Right? So inputs will be multiplied and the output will be taken. Right? So that is how the AND gate is working. Is that clear, everyone?
Yes, sir.
Right. Okay. So the last one we have, which we call OR gate. Right. So the symbol goes like this. So A is here, B is here. The output indicate as A plus B, which we call a Boolean addition. Right. And if you think about the truth table, combinations of A and B are not going to change, but the output is slightly different from the mathematical addition that you know. Slightly different. In most of the cases, it is same, but some of in one specific case, it is different. So we know the combinations, right? It's 0, 0, 0, 1, 1, 0, and 1, 1. Those are the combination that is possible for two inputs. No any other combinations can be found, right? So since the addition happens here in the first three lines, that means 0 plus 0 will give you a 0 as mathematical addition. 0 plus 1 will give you a 1, same to the mathematical addition. 1 plus 0 again give you a 1, similar to the mathematical addition. This is the place where it goes different from the algebraic mathematical, so like the algebra, right? 1 plus 1 here, according to the communication problem has happened, people. Can you hear me clearly, everyone?
Yes, it's clear. It's clear.
Right. Right.
Yes, yes, sir.
Okay. So the 1 plus 1 will give you a 1. The reason is this 1 indicates the value true, right? And a 0 indicates a value false. So that is why 1 plus 1 true is adapt with a true is again will provide you a true. That was the logic that they are using, right? So that is why they have taken 1 plus 1 as 1, right? So that is what you need to remember regarding the OR gate, which performs Boolean addition. Are we clear with this, people?
Yes, sir. Clear, sir.
Right, great. So let's draw this thing, right? I'm going to, yeah, minimize it like this. So here goes your basic gates categorization. Let me know when you're done. Right. Who are done? How about others?
Done, sir.
Okay. Yeah, Rizon, you can send me the details where you have gone hard on third lesson, and you can refer the videos always, right? In case if you are not clear with the videos as well, so you can ask me, right? Anyone who is still writing?
Still doing, sir.
Okay, okay. Let me know when you're done.
Done, sir.
All right. Anyone who is still writing? All right. So now I'm going to show you how the combinational gates are being formed. Right. So these are the basic gates. Right. So combinational gates, they are going to happen like this. So when it comes to the combinational gates, the name defines it, combinational. That means combining, right? So combinational gates are formed by the AND and the OR gates by combining with the NOT gate, right? So let's see how this is happening. So the combinational gates, right? There are two types. The first one is called NAND, right? So NAND gate, first I'll show you how the NAND gate happens, right? So the NAND gate happens like this. We got an AND gate, and to the output of the AND gate, we are connecting a NOT gate, right? So what happens is when A and B is given, this produce A dot B, and NOT gate will give you A dot B total bar, right? Or we can say A dot B within brackets at the outside, we got a dash, right? But this is what is happening. But if we are asked to draw the NAND gate can be drawn like this, right? It has one single symbol, right? The single symbol is drawn like this. In front of the AND gate, we will connect the dot of the NOT gate. So here we say A and B is produced. A dot B's total bar is the output, right? So this is the nature of the NAND gate and the symbol of the NAND gate, right? And if you think about the truth table, it is happening like this. So you got A and you got B. So here you are going to check A dot B's total bar. Right, and we know the combinations. It's going to happen like this. And A dot B's total bar, that means 0 into 0 will give you a 0 due to the multiplication, but it's multiplying, then inverted. A dot B indicates multiplication, bar indicates the inversion. So 0 into 0 is 0, inverted, it will become a 1. 0 into 1 is 0, invert it, it will become a 1. 1 into 0 is 0, invert it, that means making the opposite of, that means it becomes a 1. 1 into 1 is 1, invert it, it will become a 0. People, is that clear?
Clear, sir.
Right, great. So the NO gate, the other one, goes the same way. So the second combinational gate is NO. So how the NO gate happens? We have O gate. At the in front of it, we fix a NOT gate. So as earlier we discussed, A, B, here it will give you A plus B. And this NOT gate will give you A plus B's total bar. Right? And the single symbol can be represented like this. Right? So it will have A and B. A plus B's total bar will be there. Right? So the truth table, I think now you can figure this out even alone. We got A, we got B, we have A plus B, then after inversion, the total bar should be there. So the combination 0, 0, 0, 1, 1, 0, 1, 1 can be there. Now what's happened? It will add up, then invert. 0 plus 0, answer is 0. Once it is inverted, it is 1. 0 plus 1, answer is 1. Once it is inverted, it is 0. 1 plus 0, answer is 1. Inverted, it becomes a 0. 1 plus 1, again it's 1. Inverted, it is become a 0. Right? So that is how the NO gate is working. People, is that clear?
Yes, sir.
Right, great. So let's write it. So let me know when you are done. Okay, one is done. How about others?
Sir, no gate.
Okay, okay. Let me know when you're done.
Done, sir.
Wait, sir.
All right, people. So let's move forward. Now, since you know about the gates, let's sneak into the book and see whether we miss anything. And there are some specific circuits to be shown to you. Now we talk about the basic logic gates here. They are here talking about the AND gate. And here they have implemented the AND gate using some electrical circuits, right? So now have the idea what they are trying to talk here, right? So here the inputs, they have considered the inputs as from the switches A and B, right? So when they have these switches, what they are trying to implement is the open state of the switches indicates as 0. So 2 zeros, the bulbs are not being lightened up. So that means 0 when A is A and B, the switches are there. It's 0 and 0. The bulb is not lighting, right? As well as when both the switches are being closed, right? So both the switches are being closed. I'll put 0, 0 at the top. When both the switches are being closed, that means it indicates 1. because if the open state indicates 0, the closed state indicates 1, bulb is lighted up, right? And in the other two cases, when A is open, B is closed, right? In case like, let's assume now this is being closed, right? But still, since this is open, light will not light up, as well as when the A is closed and B is open, still bulb is not going to respond, right? So that means this kind of a circuit indicates or replicates or illustrates the operation of the AND gate. Is that clear, everyone?
Yes, sir.
Yes, sir.
Okay, so you don't need to write these things down onto your books, but it's better you understand how the things are happening, right? Okay, and they have talked about the truth table. We went through all these things, and later they are talking about the OR gate circuit. Look at this. In here, what they have done is they have taken the same logic, the switch A and switch B. So A and B is there. So we are trying to implement the O circuit using the bulb. That's great, Suzu. Right. So when it comes to this circuit, if you got any one of these switches are being closed, then the circuit is complete, right? So now in this picture, you can see the circuit is complete. So the electricity flows through the bulb, so it light up. The only case where it does not light up the bulb is where both the switches are not being closed, right? That means in 0, 0 positions, the open position is considered as a 0, bulb is not lighting up. In case any of the switches are being closed, let me take the other way around, otherwise. If A is not closed, B is closed, then bulb is lighting up. If A is closed and B is not closed, again, bulb is lighting up. If both the things are closed, still bulb is lighting up, right? Which replicates the OR gate operation, right? And yeah, people, is that clear?
Yes, sir.
Sir.
Right. And then finally, they have taken you to the NOT gate. So here they have used a different kind of drawing where they have only one switch. It is very convincing, right? Because we got just one input for the NOT gate, right? So here the A is open, that means it indicates 0. When it is indicates 0, the electricity flows through the bulb. So the bulb is lighting up. That means bulb has the state of 1. But when this is being closed, if this is closed, then the circuit will be short-circuited. That means it will find a short path to flow. So since this is a shortcut for the electricity to complete its circle, a very negligible current or a very minimal current which flows through the bulb, which is not sufficient to light up the bulb. So that means when A is closed, bulb is not going to light up. Do you get that, people?
Yes.
Right. So that is how the three gates are being illustrated. Right. So if we go down, the NO circuit as well as the NAND circuit are being introduced to you. Right. So we have done up to this point, people, even though the book is explaining it in very bigger manner, it's a very simple thing that you need to understand. By next week, we are going to design this kind of circuits, right? And first of all, we try to take out an output from this kind of a bigger circuit. Later, we will design this kind of circuits due to a given expression, right? So let's learn about it by next week, people. So till then, I'm going to end the session from this point today, since it is 5 o'clock, right? So thank you very much, everyone. Yes.
Thank you, sir.
Welcome, sir, and thank you, sir.
Right, okay, everyone. Thank you very much. Sanushi, I will clear the things for you. Just wait, right? Others, you can leave. No worries. Thank you very much, everyone. Have a very nice day and a good night.
Oh, yeah, sir. There was
Thank you, sir. Goodbye.
Right, okay. Okay. Thank you very much, everyone. Thank you.
there was a nice.
Right, okay, Buddha. Everyone's all right. Yeah, Sanushi, it happens like this.